Excellent talk. Moving on to the next presentation, this is from the side of Forth. Vassilis Papaefstathiou will be the presenter. He's a faculty member at the Computer Science Department at the University of Crete and also an associated researcher here with our Laboratory of Computer Science, Computer Architecture. And in the EPI project, he has been the principal investigator and has led the team that created the last level cache design being used in the RISC-V chips of the EPI projects, likewise for EU Pilot. Vassilis has a range of interests around computer architecture and performance optimization and analysis, and he will give us a retrospective, his own viewpoint on the progress of prototypes within the EPI project.
Okay, so hello, good afternoon. This is Vassilis Papaefstathiou from Forth. Thanks, Manolis, for the introduction. So in this talk, I'm going to give you a kind of retrospective on the design of the memory hierarchies that we've built over the years in several RISC-V prototypes, mostly in the context of the projects here, EPI, EU Pilot, and Riser. So the term memory hierarchy here is a bit, more relaxed, so it includes parts of the core of the design. So let me start a little bit with the evolution. So mostly I'm going to talk about EPAC and the specific part of EPAC, the VEC part that you've seen already in multiple presentations these days. So the evolution here, everything started at the end of roughly 2019. So we built a team around Stream 3 to make EPAC 1.5. It has been a very tight schedule at the early beginning, something like 20 months from the start of the project to the tape out. And I can tell you that some of the partners started with a blank sheet, nothing, right? No code, nothing to reuse in terms of code. It was only know-how. So it was really, really tight. We collaborated very closely with all the teams. You will see all the teams. You probably know all the teams, but just to mention here, and the target here that was taped out in 2021 was EPAC 1.0 with the VEC, with the long vector architecture, the out-of-order core, the Avispado core from Semidynamics to wide in-order core, the wide VPU, 256 double precision elements, and the contributions from the side of ETH and Fraunhofer on the stencil accelerators, and the VRP from CA, the variable precision arithmetic unit. It's also RISC-V, so a heterogeneous thing, multiple different cores and architectures there. We targeted the Global Foundries 22 nanometers technology, taped out 2021, and we follow up with another tape out on EPAC. We call it 1.5, mostly enhancements on EPAC. That was taped out a year later, and in October 2022. And you've seen this several times over presentations, booths, events, summits, workshops. And now the latest incarnation, all the generations of this hardware and the logic and all the partners that work together is on EU pilot, the EU pilot VEC, and the part of VEC that continues in the last parts of EPI. And is also, again, the MLS, which is the evolution of all the STX and machine learning and stem cell accelerators. A new technology is like tick-tick-tock or something like this, modifying the architecture and then changing the technology, going from 22 to 12. And for the case of MLS, you've seen that it's already at 7 nanometers. That has been taped out a few weeks ago, 3 weeks ago. So I'm gonna, without further ado, I'm gonna go directly to EPA code 0.5. So what is this? Here you can see on the right a kind of cartoonish depiction of what is there. Is like a multi-tiled architecture, 4 VEC tiles, 1 STX tile and 1 VRP tile with some I/O. So the VEC part, it's the Avispado from Semidynamics, the VPU from PSC and with the floating point units of Unizagreb, the L2 and home node from Fourth and Chalmers respectively, the NOC with the cross points, the 2D mesh NOC with the cross points from Extol. So this consists of the building blocks of all the chip at the beginning, the APAC 1.0. And there are details. You already know about the wide VPUs. It was the RISC-V vector version 0.7, and we had this shared last level cache and banks with coherence based on the CHI, as we'll see a few more details. The STX, we mentioned already about the stencil and neural accelerator, the VRP, and now it's the NOC and the chip-to-chip link from Extol. It's a 2D mesh CHI-based NOC, very wide, 512-bit data channels, one for the receive and one for the transmit, so you can double the numbers. And the chip-to-chip link is 8-lane SERDES on the side that connects to the outside world of the chip, more than 10 gigabits per lane, 8 lanes here, so around 80 gigabits and a bit more. And this chip-to-chip link extends the CHI of chip, so we can do things outside this chip. Why do we need this? Because this chip does not have a DRAM controller, it does not have a memory controller. So we need somewhere to access memory, and that's outside the chip. So this chip is actually tethered with an FPGA and hooks on the FMC of a VCU 128 FPGA. The daughter card was built by E4 in collaboration with lots of partners, of course. And there is a custom design inside this FPGA that allows the chip-to-chip link to provide access to DDR, to HBM, to Ethernet, to UART, and there is a PCIe endpoint to have control from the host. So this is more or less the beginnings of EPAC, the first chip and the VCU. Now, if we go into the details about the memory hierarchy, so we started at that time and said, okay, we're gonna make a coherence protocol. Yes, which coherence protocol? 25 out there. We could make the 26th or maybe the 126th. So we started looking around and we said, okay, let's not redo all this work from the beginning. Let's adopt something and see how to customize it on our needs. So what we did at this stage was to adopt the AMBA5 CHI protocol. It was issue B at that time and went a bit to issue C. And one of the things we did, we selected the subsets of the protocols that the opcodes that we needed for our purposes, and then built all the hardware based on this. It was close collaboration with a lot of partners working on this memory hierarchy. Semidynamics for the L1 caches, because they have the part of the caches, then they have to do what is called in CHI the request node full, the RNF. Fourth and Chalmers created the HNF, which is for the home node and maintaining the coherence. Extol had all the protocol transportation over the 2D mesh NOC. So this is how it started. And I think it was a wise decision to go with this protocol. We also did over the customization, actually, we kind of diverted in the physical, in the implementation in some of the things. It's not that it has to be like this, but we took some decisions and it was, I think, better. We changed a little bit the approach of protocol deadlock avoidance. So we added a few more channels to have some flexibility. It's a kind of not very secret, but it's our own sauce here. And this has been done in collaboration with all the partners and NCA at that time, working on parts of communicating with the external parts for the common platform. Now, this cache, it's configurable, but the cache and home node, it's distributed slices on a NOC, so you have multiple different places. The size is actually dictated by the area that we have and how much we need to devote for this test chip, so it's a test chip. And we went to 256 kilobytes per slice. 4 of these slices you've seen earlier in the design that we have 4 vec tiles. So each tile has its own distributed part. It's a tiled architecture. We copy and paste, let's say. It's not that simple. And copy paste. When you copy paste, you do mistakes. And this has happened actually. So it's a 8-way set associative cache, pseudo-LRU policy, lots of things. The idea is that all these designs, we're going for high bandwidth. So it's the peak you can do 1 cache line per cycle per slice. So do the best if you run at 1 gigahertz, that's 64 gigabytes per second. It can saturate multiple DRAM channels, and it can even saturate a single HBM channel. If you go even at 1 gigahertz, if you go further in the frequencies, you could even saturate more. So for every slice, we got this decision. We wanted the on-chip hierarchy to be very, very fast. I think it's very good what we did, and it really works with a long vector architecture, which has a lot more pressure in the memory hierarchy. There are also other things that can be tuned, like the interleaving mode. So how do you distribute the cache lines inside the network on chip at the slices? You can do it per cache line, and I'm going uniformly all around the chip. For a long vector, 256 elements is something like 32 cache lines. So you have 32 cache lines, and you might bring them from the chip multiple times and fetching around the NOC multiple times. Or you can do other things like 2 kilobyte. The 2 kilobyte is the reason we did it, because it's a vector length size. So you get all the vector from the same cache slice, or 4 kilobytes, which is actually 2 vectors, 2 full vectors of 256 elements, but the 4 kilobyte is the operating system page. So you can even start playing around with policies in the operating system on where to allocate these pages so that they map to your closer, parts of the memory hierarchy. Though lots of freedoms, lots of programmability. I'm glad we did all these things, because they proved at some point that they work. Another thing is that there is additional support for atomic operations that is happening far in the memory hierarchy, what the CHI calls far atomics. So it doesn't, the atomic operations do not really can happen in the core, but you can offload the atomic operations to the home node and the last level cache. So you're doing something like fetch and add, and it happens in the actual cache, not inside the core. And that has been really helpful. Of course, we also support the load reserve store conditional. That has been kind of complicated to prove forward progress on these things, because they need to have the proper properties. And in terms of performance here, we have multiple outstanding misses, coherence transactions per slice, another 64 outstanding writebacks per slice. So in total, you can count something like 512 outstanding transactions to DRAM from all the chip. It's a relatively big number. Also supporting other things like cache management operations, cache allocation hits by cores. You can support non-temporal loads and stores, because sometimes there's no locality when streaming data. And other tricks that helped us in the process was that we had support at some point to configure the caches to behave as scratchpad, and that proved very useful at the early stages of the bring-ups of the chips, where we did not have access to the external memory, so could turn all the internal SRAM arrays to memory and then start doing bring up in parallel. So trying things to the core with all on chip memory and then going out. And just to mention a little bit that for the 2D mesh from Xtol, I said there is a 512-bit data channels for high bandwidth, and there is also multicast support for snooping inherent in the NOC. And as we said, the chip-to-chip link to get access to memory and I/O. Now, okay, we started building this. it took us several months, integration meetings, hackathons happening, all of us together. We had COVID in these times. At some point, it was a bit more difficult to meet. But once this started moving and using the FPGA SDVs to do a lot of testing, the emulation that we had available. So things started working, and we started to have Linux booting, doing things. Functionality was the first goal at that time, and then we started to see, okay, let's optimize now. And we have these regular meetings every Thursday that are happening the last at least 5 to 6 years, 12 o'clock CET, where we meet and discuss. And in one of the meetings, where we're getting closer to have things working. Things were working, but have been evaluating. There's Jesus coming and say, "Oh, I don't get the performance that I want. I mean, supposedly you should get 90% of the performance." And then we start with this tool. We started digging deeper. So this is actually screenshots from our meetings, March 2021. So this is a stream copy, right? And that does, what do you do? Vector load to load and vector store to copy. So there are here, this is a 2 kilobyte vector. So this is 2 cast lines requested back to back, and then you do something. Hopefully in stream copy, you do nothing. It's a load and a store. And then you start storing another 32 cast lines. This goes all over the NOC, depending on your interleaving. So things get crazy, and see, okay, where do we get here? Supposedly you should get something like the peak, 64 bytes per cycle. How much we get? We get 25.6 bytes per cycle. And this is the designer's view, actually. It's not for the users. So it's all the protocol here running the vectorized stream over Linux, right? And then we started digging deeper and deeper and deeper. And when you dig deeper, you start seeing, oh, here are the loads. We have 12 idle cycles and then another 60 idle cycles. So what's happening here? So everything is pipelined, but what do we have bubbles here? Why this gets delayed for 9 cycles? It should be 2 or 3 or 4. So there are very, very low level things where we get all the designers together from the main blocks and all the people that are testing the software, and we have been optimizing all these things at a very cycle level just to get the best that we can. So this is a screenshot before the tape out. It was like very early, and we keep improving and improving and improving. I could be explaining you for hours what has been happening here, and lots of slides. So this meeting started for 1 hour. It took, I don't know, 2 hours, then repeated another 2 hours, another 3 hours, and kept going. So this is what we can call the nanoscopic view, right? Jesus was presenting the microscopic view with paraver traces. And after the microscopic view, we have to go to the nanoscopic view with the cycles and see what's happening. So we did this for this, trivially would say someone stream copy kernel, but we found, okay, if you're not careful, you lose things here and there and get to 40% utilization instead of having, I don't know, 95. So yeah, this is a snapshot of the history of things that we did, and we keep doing for certain parts of the designs, and trying to squeeze the idle cycle. Some of these things cannot be easily fixed. They might require redesign of many things. That was 2021. After that, we had designed things and things again. Certain parts, the core, the caches, the VPU, many things. Now with this thing, we went to do physical design. So you can see the physical design of the whole chip, the EPAC 1. Zooming in the micro tile here, for instance, you can see the vector register file with 8 lanes. The target was 1 gigahertz. So these are just to show you. And then chip came back, packaging, testing, and boom, hello world, September 2001. A famous picture. It has been posted in the website. Communication, dissemination. So it was intense breakup sessions between, I don't know, board bring up, then chip bring up, fourth X-stall doing different things at different times, but this has happened, in this building upstairs, 2 floors. I can show you the room. Here is the first chip, and what has happened, we actually went even off specs, like going up to 1.4 gigahertz over let's say, boosting the frequency, but because 1 gigahertz is another corner, we could cool the chip and could try many things, and it worked pretty well. So, and then we started, doing more and more things in the bring up. So some things work first and other things later. And then in the EPAC chip, we started with the bare metal, and here we have AXP with the vector, and you see the speed up of 25x, which is the 30x that Jesus was saying. So we only have 8 FPUs, but you get the speed of 25x. So this is one of the, let's say, insights and what long vectors can help in certain cases. Now with this thing, we don't stop there. We can confirm what we have been seeing in simulation in FPGA design. So this is at 1 gigahertz running vector stream on the design in all the on-chip cache hierarchy. So here is like the copy gets you to 32.7 bytes per cycle. Let me do it like this because 64 is the peak. And using performance counters, you can draw all these things from the memory hierarchy and getting them live in our prototypes. Here you can see the behavior in terms of megabytes per second, so gigabytes per second. So this is the write bandwidth, this is the read bandwidth, and the aggregate is the green. Some of these things overlap, and based on the kernel, you see, scale does not work pretty well. What's the problem with scale? There was some particular problem not in the memory hierarchy, but with the implementation of scale, and we had this. We could see this, and we could see this at many places. And of course, by the way, given that we have this, we also have power analysis in the boards. So we have, let's say, ways to capture the power the power consumption of the chip in certain cases. So doing fine tuning, we could see how the power scales. When you run stream copy with one core, then you turn on another core, you turn on another core, you turn on another core, all of them doing stream copy together, and this starts speaking. So with all these prototypes and all the things that we put in the boards, all together, the stream team, the stream 3 teams and the designers, we can do many things. We've done many things. We understood many things, and we learned many things. So, and with these learnings, and actually what has happened with this chip was that there was an unfortunate case that we could not use the high performance network when getting out of the tile. So inside the tiles, everything was fine. In the top level, there were some unfortunate issues with some EDA tool. I cannot say more. And then we could not get the full performance out of the chip. And then we went to EPAC 1.5. So it has happened quite soon after the first bring up of the EPAC 1.0. EPAC version 1 has been enhanced with lots of things. You see, a year later, we go to a second tape out, and the thing is that there has been several enhancements, performance improvements, and fixes, of course, in the core. And then what has happened is that the cores get a little bit fatter in terms of area, and we have specific area budget, and now we have to decide what to leave out. And what has happened is we left out 2 cores. So the rest of the memory hierarchy was the same, but now this chip had just 2 cores and GPUs instead of 4 in the previous version. However, I mean, things got, these are the developments for 2001, 2022, and you can see, the physical design, and then the chip comes back, we mount it on the board, we mount the socket on the board, we mount the chip on the board, we put the board on the FPGA, and this is the full setup of the bring up that actually is upstairs, 2 floors up, 1 floor up in our electronics lab, where we did locally our part of the bring up, and preparing all this and testing. It has PCI connectivity, lots of things are happening. So what has happened in June 2023 is our first Linux boot with EPAC 1.5. It was a Linux 0.7, RISC-V vector, version 0.71, Ubuntu 20 LTS, the root file system on NFS SSH, and actually this is a GUI that we got via VNC from the chip. So you can see a normal window manager, and then terminals. You can see the cores and the extensions. And here in this quarter, it's Limpac running over a GUI on the EPAC 1.5 chip. So it ran the vectorized version of Limpac, and it was like I think one of the major successes here, the EPAC 1.5, and so many things went well, and so many things are working and have matured even 1 year after the first tape out. So it's really amazing. And after that, this has happened internally in June, and then there is a point in September 2023. Is the first presentation of this, outcomes to EuroHPC. On the top right is the meeting on EuroHPC. Etienne Walter was there. Myself and Filippo were remote. Jean-François Blanc was also remote. So we have been presenting to the officers this. And after this, it was really good. It has matured, many more things done, doing live power consumption. And this was the beginnings of the EPAC 1.5 World Tour. So this thing has started moving and been presenting in RISC-V Summit, EU Summit, lots of events. So I think it marked a major milestone of EPI SJ1 and 2 at the same time. And so it's in use from many projects, from many SDVs. You can get access to this via the SLARM platform at BSC. And now, of course, developments keep going, EPAC 2.0 or EPAC VEC for EU pilot, but the use of this chip did not stop here. So what has happened, it's another project that's coordinated by Forth, by Manolis Marazakis, our host here for the co-design, and lots of partners from EPI. So using the chips from EPI, the EPAC 1.5, there have been a few more prototypes being created. Initially, this EPAC 1.5 is an accelerator, right, hooked to the PCI. So this is a bit better form factor with a different FPGA for riser. But one of the more important parts is that we added a few more things to go from an accelerator to a microserver. What does a microserver mean? It means that you want to do standalone boot. And what has happened is that we changed a few FPGAs, we got some connectors, we got an SSD, and we started with a variant of the EPAC FPGA design that you've seen later. The chip here, chip-to-chip link, DDR controllers, gigabit Ethernet, UART, whatever was there, and some control logic as set point. So these are variants of the EPI FPGA design. And the next step was to make it standalone. So extended this with a system controller. So similar in order to control the boot process of all the chip. Add an SD card so that we can have images to load in memory. A PCI root complex from Xilinx so that we can hook to NVMe drivers and whatever else can be hooked there. And 100 gigabit Ethernet in progress. So this is developments from 2023 to 2025. So getting from this to a microserver, and actually would say that we don't need an external host. And there is the host is this mini core, the CVA6. It's a mini system controller, very similar to the fabric controller that exists in the IO tile of EU Pilot. It's not the same, but similar concepts. And then with this, you start doing nice things. When you power up, the mini the system controller starts in a boot ROM. It goes into the SPI card, loads things in memory, and now initializes the link, initializes the chip, and then the chip starts running. Linux, which initializes the PCI root complex, which reads all the root file system from disk. So this is completely standalone. You don't need network. for this. And we have a prototype of this also upstairs, and a lot more details. But I just wanted to say that the capabilities of EPAC 1.5, even with some minor limitations here and there, allows us to build really big systems and real systems. Having all the functionality, having all the drivers for PCIe on top of Linux, for instance, and 100 gigabit Ethernet, and many more. So this is the work keeps going. So this chip is very useful for many things. And now it's the part of the EU pilot VEC. So actually, what has happened here is that it builds on EPAC 1.5 actually, and what happens here is that we have a lot bigger chip, a new technology, 12 nanometers FinFET. So we can fit in a chip that has been taped out actually 8 V tiles, so more cores and more advanced cores actually, as we will see. Now the other thing is that this chip has its own DDR memory controllers, so it can be standalone. There is a lot more area we can afford to put these things. So 4 DDR memory controllers, 5 chip-to-chip links with 32 gigabit PS per lane, one CXL or PCIe 5 PHY, an interface here to operate either as an endpoint or a root port. And now the V-tile is the newest version of the semi-dynamics at Revito Core 3, way out of order, RISC-V Vector 1.0. The newer version of the VPU from BSC, which is the EVA architecture, and advancements in the level 2 and home node, as I will show you a few more bandwidth optimizations and interchip things. We'll talk a little bit about this quickly. And the crosspoint is actually lower latency with lots of optimizations, and also extending the NOC with the chip-to-chip links to something bigger. So what has happened here in the memory hierarchy? Instead of 2 4 cores, we have 8 now per chip. Newer and more optimized operations via CHI and by adopting new versions. And now it's improving bandwidth and latency. So it's at Revito with gazillion misses, 128 outstanding misses from the core. The L2 got more outstanding transactions per slice, 128 coherence transactions of misses, plus 128 writebacks to memory, plus some things about I/O. And if you multiply all this together, you will see that the memory hierarchy of this chip allows you to do around 2,000 outstanding transactions to memory. It's a very big number. I'm not sure if the memory controllers, the LPDDR memory controllers, the LPDDR memories could be able to answer such potential response from the cores, but I think it's a very interesting design, and it has many things. So it has other optimizations like direct memory transfer, so getting shortcuts in the NOC for responses that are we're getting from memory. And more importantly, the last part is the supporting coherence across what we call chiplets or chips or sockets. I'm not gonna differentiate between the two, because what we've done, essentially, we started with the concept that we will build this thing as a chiplet and we'll connect more of them. Of course, the budget of the project was not enough at that stage. We were expecting things to improve and have lower cost, but it didn't happen. So the same mechanism can be used to connect chips, dies, if you want to call it, or sockets. It doesn't matter if the chips are on the same board or are sockets on a multi-socket baseboard like UBB. So the same mechanisms can be used. The latency might differ, but it's what we have here. And of course, there are other things that are kind of interesting here with as you grow the memory hierarchy with the 2D mesh. One thing is the interleavings. In our case, the interleavings are programmable, but in this chip, the default where you can change is to actually traverse the NOC. If you start from here and start requesting a long vector, what happens is typically you're gonna go around the chip and start asking for gas lines like 4 times with 8 cores. Now Here, what we do, we change the order. It's a modified Morton order, a Z order. So it goes like this. So if you start fetching, it will localize the traffic first here, then move the localized traffic here, and keep going around. This is a part of the interleaving. Of course, can be programmed, but this is one of the things that we hope that it can help lots of applications. And the other thing is the interleavings when there is a cache miss. When there is a cache miss, there are, the last level cache DL2 has to go to memory. Which memory? You have 4 memories. You can start interleaving across the memories. We don't think that this is useful. And actually, it's still programmable. What we did, the default is that the 2 caches, when they have a miss, they send requests to their closest memory controller. So the missed traffic localizes here, another one localizes here. So you don't get to have uniform traffic across the NOC for many of these of the patterns, depending on where you go. Now, moving further, so one of the ideas was to aggregate chiplets, dies, or chips. So what we have done at the very beginning, even from the proposal, we have said that we want this to scale, and it was designed to scale. It is designed to scale, and regardless of if we call it a chiplet or a chip or a socket, so we have all the mechanisms to aggregate multiple UPilot dies and make it appear as a single die. It's not monolithic, but make it appear in software as a single thing. So for this, we have global address space across the chips. We use the chip-to-chip links, and here it's a fully connected topology with 4 UPilot tech chips. And you can also program the interleavings. So every core on every chiplet can access the memories of the other chiplet. And here, actually, what we want to achieve is to make it appear as a single monolithic chip in software and put a single instance of Linux across all these chips. It's like multi-socket NUMA, but it can be multi-chiplet NUMA or multi-die NUMA. And actually, what we've done here is we have inter-chip coherence. So we extended the mechanism that we have here across the chips. And there are many ways to do it. We chose to go to the something that would not require major changes in the chip. And what happens here is that if you have a cache access from the core and goes to the local level 2, if there is a miss, goes to the local memory controller, returns back to DL2, and probably gives back the data to the core. Now, when you access an address that belongs to a remote chip, what happens is that you don't cache this cache line remotely in your last level cache of this chip, but you are actually caching only in the L1 cache. So you can go over the chip-to-chip links, go to the proper, based on the interleaving, to the proper cache. If it's a miss, it might go to the DDR, and then it gets back to you. And this L2 and the home node keep track that there are sharers in remote chips, and when it's needed, it will generate the appropriate snoops. So actually, it has been designed like this, and with the intention to scale. And of course, depending on the platform, now the platform is that these things can happen on a UBB when properly connected. So of course, the first thing is to have the chip up and running, and then there's a lot more opportunities to test and try more things on this front. So it took a little bit longer than expected, but thank you for your attention. I would be very happy to answer questions.
Questions for the speaker? Any reaction from? Yeah.
Thank you very much for this very interesting presentation. I just want to ask, yes, when you were talking, for example, about the interleaving, how did you make the choice? So did you have like a benchmark or test that showed what performed best? Could you comment a little bit on this?
Yes. So generally, the 2D mesh have certain good properties, but if you look at their capabilities, they depend on the traffic pattern. So when you go into the uniform traffic patterns on 2D mesh NOCs, the larger the NOC, you start to get a lot of contention after some percent of utilization, depending on the size of the network. That could be starting from 10% if the NOC is very, very big. So doing uniform random accesses across a NOC, even at 10%, injection rate, the network gets saturated if it's like 8 by 8. Now, if it's smaller and depending on the traffic pattern, there are lots of traffic patterns that the numbers vary. So here, what we try to do is to avoid having uniform traffic scattered all around the chip all the time. So by default, you will have it, but we don't want to have it. We want to have it in a form of controlled and staggered matter, predictable. So if you pick your interleaving hash function with XORs, which is very common, then you don't know what will happen. You cannot reason for anything. We can change it. It's programmable, as I said, but we prefer something to be deterministic. And if it's deterministic, it can be understood by applications, and the applications could make better use of their access pattern. That's the idea. Of course, there is no silver bullet here, but we expect some things to be better.
Thank you.
Any other question or comment for the speaker? If not, thank you, Vassilis.
Thank you.
Warm welcome for him. We can take a short break, like 10 minutes for a refreshment and coffee, and then resume.